My name is Ivan. My metric number is 188024. Today we are going to talk about hydrofluoric acid alkylation process. Okay, first of all, alkylation process is a transfer of alkyl group from one molecule to another molecule. This process is used to produce a gasoline range material from olefin. So this is most common process in the petroleum industry, and this process uses hydrofluoric acid as a catalyst. Okay, these catalysts will lower the temperature and also the pressure. Okay, by using this diagram, we can understand further about this process. The light olefin isobutane will fed into the reactor. Inside the reactor, hydrofluoric acid acts as a catalyst. So the reaction will happen, and then the product will go out from the reactor. So the product will go to the acid settler. Inside the acid settler, the acid will settle down at the bottom of the acid settler, and then will go to the acid purifier to recycle back to the reactor. The balanced hydrocarbons is flow through the fractioning mechanism, which is deisobutanizer and depropanizer. So inside this fractioning mechanism, it is fraction out the alkylite and also the propane, whereby the isobutane is recycled back to the reactor back. For further process description is discussed in the process flow sheet.
Assalamu alaikum. This is the process flow sheet. So now the feed is subjugated to drying followed by pre-cooling. After the pre-cooling, the reaction mixture is fed into a reactor. Unlike the CSTR, we are using the impeller reactors, and in impeller reactors there's cooling tubes to absorb the heat generated, and then afterwards the reaction products enter a settler where oil and HF are separated. HF purified will be recycled back to the reactor, and then HF stripper is used to remove the HF in lower quantities from the alkylate products. Eventually, the HF stripper produces HF that is sent back to the reactor and the alkylate product. The alkylate product is sent to a diisobutanizer and the depropanizer unit. And the final alkylate product is produced by using a defluorinator, which is basically a caustic wash or adsorption unit. Finally, the N-butane and alkylate is produced as the bottom product. As we can see here, the N-butane and the alkylate are produced.
Now I will proceed with the hydrofluoric alkylation process reaction mechanism. So this reaction is involved the formation of carbonium ion. The first step is the initiation step, which the transfer of proton from the acid catalyst to the olefin follicle, and then the process followed by combination of the isobutene to produce tertiary butyl cation. The next step is the propagation step. The tertiary butyl cation will reacting with the olefin to produce a larger carbonium ion, and then which then abstract hydride from isobutene molecule. The hybrid abstraction generates isoparaffin with a new tertiary butyl cation to carry a new reaction change. And the last step is the isomerization step, that allowing 1-butene to isomerize to 2-butene, that will reduce the production of dimethylhexane and thus increase the production of trimethylpentane. The next step is the type of reactor used in this process. So there are 4 steps to design reactor. First, removal of heat reaction, generation of acid surface, acid composition, and introduction of olefin feed. So this is the reactor introduced by Phillips. This reactor is acid settler cooler reactor. Section is critical for good conversion in hydrofluoric acid alkylation system. And then this reaction is almost similar to horizontal shell and tube heat exchanger with cooling water to maintain the reaction temperature at desired level. And then by using recirculating pump to force the mixture through the reactor at to 10 times the mixed hydrocarbon feed rate to the reactor. The good mixing is attained by this process. And lastly, the acid circulation in this system is gravity differential. So we don't need to buy a expensive circulation pump. I think that's all. Thank you.
Okay, so alkylation reaction catalyzed by strong acid, either sulfuric acid and hydrofluoric acid. Hydrofluoric acid alkylation has been used more commonly in petroleum refineries, and it can be more easily regenerate than sulfuric acid in the alkylation process. It also less sensitive to temperature fluctuation than sulfuric acid alkylation. After the product was obtained, the hydrofluoric catalyst is regenerated on site. Therefore, in our process, we use hydrofluoric acid as our catalyst. Next, general operating condition for our process. The presence of olefin with butane will lower the octane number and increase the acid consumption. The table shows the octane number of alkylate produced from light olefins. Major variable for alkylation process is reaction temperature, acid strength, isobutane concentration, and olefin phase velocity. For reaction temperature, for hydrofluoric acid alkylation, the reaction is less significant and is between 21 and 38 degrees Celsius. For acid strength, the minimum acid strength required to operate the system should not be lower than 85 weight%. To provide a sufficient margin of safety, acid strength is kept around 90 weight%. For isobutane concentration, the external isobutane to olefin ratio is kept between 5 to 1 and 15 to 1 in industrial operation, while inside a reactor with high circulation, this ratio is kept between 100 to 1 and 1000 to 1. Lastly, for olefin phase velocity, velocity of olefin is the value of olefins per hour and also defined as the equation given. High olefin phase velocity increase formation of acid sulfate, which are corrosive to downstream fractionation facilities. Using this formula, we can determine the product quality. We can see that olefin phase velocity and ratio of isobutane to olefin does give high significance to product quality. Higher F is better product quality. That's all for my part. Thank you.
Okay. Hi, Doctor. So I'm Shakira. I'm going to present the market information. So hydrofluoric acid keep on having high demands, and it actually increased by ongoing trends within the petroleum refining industry, because as we know, HF acid alkylation produces gasoline. So one of the largest integrated energy company in the US was capitalized in Houston, Texas. So based on the 2014 data, the gasoline consumption is 1 to 7.82 thousand barrels per day, and it actually the highest one is from USA lah. Continue with China and Japan. So this ongoing expansion of fluid catalytic cracking actually produce more alkylation feedstock, but then it actually give us more complex and problematic alkylation feedstock. So this requires the hydrofluoric acid to be more flexible in handling increased and verifying feedstock. If we want the hydrofluoric acid alkylation to still be relevant in the future, we need to handle this problem. That's all from me. Thank you.